So in this video, we'll do one more example and then I'll try to justify the method for solving separable equations. So here we have to solve the differential equation dy dx equals 6x to the power of 5 minus 2x plus 1 all over cosine of y plus e to the power y. So as before, what we're going to start off with is we're going to multiply both sides of the equation by dx. And so what we get then is the dx's cancel out. So on the right hand side, we get dy equals, and I'm going to split this up as 6x to the power of 5 minus 2x plus 1 all over 1, and then multiply that by 1 over cosine y plus e to the power y dx. Then our next step is to bring all the expressions with y to the other side, and I can do that by multiplying both sides by the quantity. So I'm going to multiply that times cosine of y plus e to the power y. I'm going to do that on the right hand side as well. And then the equation that I get is cosine of y plus e to the power y dy, and that equals 6x to the power of 5 minus 2x plus 1 dx, right? Because this cosine y plus e to the power y cancels out this factor here. And then we're going to integrate both sides, and we then get antiderivative of cosine of y dy. That is just sine of y. And the antiderivative of e to the power y is e to the power y. And then I'm going to hold off on the constant of integration because that will show up on the other side. Antiderivative of 6x to the power 5. Add 1 to the power for the power rule, and then divide by that new exponent 6. So this is x to the power 6, and then minus x squared plus x, and then we have a constant of integration. Now, note that when we did integration here, we didn't have to use any difficult integration techniques, because when we integrated this, our constant of we're integrating with respect to y. And furthermore, you can check your answer by taking the derivative of this with respect to y. You get cosine of y e to the power y. Here on the right hand side, take the derivative with respect to x. You get 6x to the power 5 minus 2x plus 1. And so this function cannot be explicitly solved for y, so we're going to just make this our final answer. So let me So that is our final answer. And on an exam, I will let you know that an implicit solution is fine. so that you don't have to or try to figure out how do you solve this for y. So let me write that down here on an exam. I will let you know when an implicit solution is fine. So then you don't have to solve for y, which is not possible in this case. Okay, so finally in this video, I'll show that what we did in solving separable equations, the multiplying by dx, is actually valid. So remember, dy dx is Leibniz notation for derivative. It does not literally mean dy divided by dx, but this little trick by canceling out the dx actually works, and I'll show you why that is. So suppose that we have two differentiable functions, capital H and capital G, such that h of y equals g of x plus c for some constant c, and y equals y of x is a function that depends on x. Now let's differentiate both sides of this equation with respect to x. So I'm going to have dx of h of y equals dx of g of x plus c. So dx of h of y, and then ddx of g of x plus c. Now on the left hand side, we're going to have to use a chain rule. So we're going to get the derivative of the outside function, which is h prime of y, but I have to multiply by the derivative of what's inside, and that's dy dx. And then on the right hand side, that's a little bit more straightforward. The derivative of capital G of x is g prime of x, and then the derivative of a constant is 0. So now I have h prime of y dy dx equals g prime of x. I'm going to call capital H prime of y, I'm going to call that h of y, and I'm going to call the capital g prime of x g of x. So in other words, h of y is an antiderivative of little h of y, and capital G of x is an antiderivative of little g of x. And so if I write that out, I then get h of y times dy dx equals g of x. Now, assume that h of y is not equal to 0 and divide both sides by h of y. So what I'm getting then is, so I'm going to divide by h of y. I'm going to divide that by h of y. And let me rewrite that slightly. I get that dy dx is equal to g of x times one over h of y. And notice that I now have a separable differential equation, and I can call this 1 over y, I can call that p of y. So I'm going to rename 1 over h of y with p of y, and my separable differential equation is dy dx equals p of y times g of x. So what we have shown is that if this is your differential equation, that is equivalent with what we started out with, that h of y equals g of x plus c. That's the method of solving separable equations.